Alright, so let's start this lesson with a little warm-up. So let's draw a free body diagram for the following situation. So we have a football that is moving upward and rightward towards its peak after being booted by the punter. Do not neglect air resistance. So why don't you take a moment here and sketch out what you predict this free body diagram will look like, and then I'll draw it here momentarily and we'll review. Alright, so we are drawing a free body diagram, so we're assuming our object has no size or shape, or we're drawing a dot representing the center of mass of the object. So there is our football. So this football is flying through the air, so we have the force of gravity acting on it, and that points straight towards the center of the earth, which is straight down. But the prompt said we cannot ignore air resistance, so it is not in free fall. So air resistance is a type of friction force. Actually, it's like friction of the air molecules acting on whatever the object is moving through the air. So the direction of air resistance points opposite the direction the object is moving. So if this football is moving upward and rightward, then the air resistance points downward and leftward. That should be a straight line for that arrow. Alright, F air here for air resistance. So there's our free body diagram. If this was a free body diagram for something falling and not neglecting air resistance, then force of gravity is straight down and air resistance would point straight up in that situation. Alright, so we're going to talk about Newton's third law. But first, you might ask, well, we've talked about Newton's second law. Well, what's Newton's first law? So Newton's first law, all it says is that an object at rest is going to stay at rest, and an object in motion will remain in motion with that constant velocity unless acted upon by an outside net force. Now again, I'm a stickler for the word net because it's very important, because you could have forces acting on the object, and those objects those forces may cancel out in such a way where then there's no effect on the object's motion. So this is just a fancy way of saying that an object's going to keep moving with a constant velocity unless there's a net force acting on it, so unless there's an acceleration acting on it. Alright. So today, Newton's third law, basically what we're going to start looking at is interacting objects. So far when we've dealt with forces, we've kind of said, alright, forces happen, and we're looking at one thing responding to these forces. Right? But in the real world, when we're dealing with forces, we're actually dealing with objects interacting each other, whether that be by direct contact or by indirect contact, or I shouldn't say indirect contact, indirect influence. So Newton's second law is not sufficient to explain what's going on when there's more than one object interacting, which is technically always going to be the case. So Newton's third law helps us describe what's going on there. So basically, when objects are interacting with each other, then we have, let's say we have direct contact here. If we have object A pushing or pulling an object B, then object B pulls or pushes up back on object A. So for example, if we have a hammer interacting with this nail, this hammer exerts a force on the nail to the right, but also this nail exerts a force back on the hammer to the left. So it's kind of like, I don't know, if you were to slap your hand against the table, right? You feel that force of the slap because, in effect, what's going on is the table slapping your hand back. It exerts a force back on your hand. So when I say an interaction, this is a mutual influence between two objects on each other. Now, when we're talking about these forces involved in an interaction, they always occur as a pair. So if we have object A exerting a force on object B, then object B exerts a force back on object A. Now, this pair of forces is known as an action-reaction pair. This is a terrible name for this. I think I go into that in the next slide. But nonetheless, this action-reaction pair occurs when we have objects interacting with each other. So kind of a long story short of this is if there's a force going on, if you are analyzing an object, there's a force acting on it, that force came from its interaction with another object, whether that be by direct contact or not. So the reason why action-reaction pairs is misleading is because this force occurs simultaneously from the interaction between two objects. So it's not like one force is the action and the other one is the reaction, right? So you, with the hammer and the nail example, you might think because you're in charge of the hammer that that force of the hammer is the action and then the nail force on the hammer is the reaction. But that's not the case because both these forces occur at the exact same moment, exact same time. So the action does not cause the reaction. So I actually avoid this terminology when it comes to these pairs. I'll either call them force pairs or Newton's third law pairs. I think that's a more appropriate name, but this is kind of common practice to call them action-reaction pairs. So there we go. So here are some examples of action-reaction pairs, right? So now, again, I say I don't like the terminology here because they say one's action, the other one's the reaction, which is incorrect. But the pictures were fun. So in the first thing here with the car, we have the tires pushing against the road, but then we also have the road then pushing on the tires. And this is what actually causes the car to accelerate, is the road pushing on the tires. Now, another interesting interaction, excuse me. So let me actually take a step back here. So in this car and the tires, this is an interaction between the tires and the road. To the right here, we have a ball being dropped from the Leaning Tower of Pisa, right? So here, we're looking at this force of gravity acting on the ball, right? That force of gravity has to come from something, and it does. It comes from the ball interacting with the earth. So the two objects interacting here are the ball and the earth. Now, as you notice here, this is not direct contact, right? These objects interacting, even though they're not in direct contact, and that's okay. That's fine. Actually, the force of gravity behaves this way. So what we actually have here, so the one force is the force of gravity of the earth pulling down on this ball, but actually there's also a force of the ball pulling up on the earth, right? That's also a gravitational force. It's kind of crazy, but that's the case. That's the way it is. It's pretty interesting. And finally, we can use action-reaction pairs, or Newton third law pairs, I should really be saying, to explain why we can have objects accelerating in space. So when we have a rocket uses combustion of gas, causing gas molecules, kind of the TLDR here, is it causes these gas molecules to expand and eject from the spaceship. So we have basically the gas molecules then also pushing back on the spaceship or rocket, accelerating it forward. So pretty fun stuff. These action-reaction pairs can be used to explain a lot of phenomena. So a common misconception I just want to kind of reiterate here. When we have a force pair of objects that are in contact with each other, they're pretty easy to identify. It's just when the force pair is long range, it's easy to misconstrue, right? So what do I mean by this? So let's look at an example of a book sitting on a table. All right. The question here is, what is the reaction pair if one of the forces is the book's weight? So we're asking, what is the quote-unquote reaction force to the book's weight? All right. So we have a book on a table. Thinking about that book, there's two forces acting on the book, right? We've got the force of gravity downward, and then the force of the table upward, so the normal force. Now, these forces are equal in magnitude and opposite to each other, so you think, oh, that must be the Newton's third law pair. But that isn't correct, right? Because we have forces caused by different interactions. So, for example, we've got the normal force acting on the book, so that's the table acting on the book. So this means that the book then also acts on the table with a force. Now, the the weight of the book is not caused by the table. The book's weight, that force, is the force due to gravity interacting of the book and the earth are the objects there. So the force of gravity of acting on the book, its force law pair is the force of gravity of the book on the earth pulling up. Right? So just be careful there, because you might think, oh, on that free body diagram, or analyzing the forces there, they're equal and opposite, which is true, but they're not third law pairs. All right? So just be very careful with that. So kind of the caveat of this is that force pairs are never going to be drawn on the same free body diagram. All right? When you're drawing a free body diagram, that is, one object and the forces acting on that one object. So those are all forces caused by its interaction with other objects, whether they be through contact or long range. So kind of in summary here, you can kind of summarize Newton's third law as every force occurs as a member of a Newton third law force pair. These forces act on two different objects, and these forces are opposite in direction but equal in magnitude. So they're equal in strength, but they point in opposite ways. So a question here. So let's suppose that during the collision between a bug and the windshield of a fast-moving truck, which force has a larger magnitude? The force of the windshield on the bug or the force of the bug on the windshield? Okay, so here we're looking at the interaction between the bug and the windshield. Now if you look, the force of the bug on the windshield and the bug and the windshield on the bug, this is actually an action-reaction pair. Right? This is the mutual influence of these objects on each other. So the force here is actually going to be the same. All right, these forces are equal in magnitude. Now, your intuition might be different, but what your intuition is telling you is actually about the acceleration. Right? The bug has a very small mass, so therefore it undergoes a very extreme acceleration compared to the heavy truck. Right? The heavy truck, its acceleration is negligible when it's affected by this collision. All right, so that's basically what I wanted to talk to you about today, so I hope that was helpful, and now we know all three of Newton's laws.